Welcome to Syntax. Today we have a very exciting episode today. We have Xenova on from Transformers.js, which is a library from Hugging Face that allows you to run AI models, hundreds of them, dozens, I don't even know how many, all kinds, in JavaScript, in the browser, in Node. And no, it's not an API that you hit and comes back. You're actually running them locally on your machine. And I've been like, you probably have seen me tweet about it because I've been playing with it like crazy lately. And the fact that you can just like run like 20 lines of code and get these AI models to run locally, it just blows my mind.
Yeah, totally. And also, if you're asking questions of your code, like, hey, why did this bug happen? Maybe you want to have a tool like Sentry on your side to reveal all of those bugs and why they happen, so that way you can go solve them. So if you want to use a tool like that, they've been an awesome partner for Syntax, and this show is presented by Sentry at sentry.io/syntax.
So we have the developer behind Transformers.js on with us today. He's very mysterious, never done a face reveal. His name is, we're going to call him Xenova. Welcome. Thanks for coming on.
Thanks so much for having me. That's a very amazing intro. Thanks so much. Feel quite honored. But yeah, that's just... I've been working on the library for around a year. I should probably check the commit history, because one of these days will be like the 1 year anniversary, because it started like midway through February in 2023. So I guess one of these days, possibly when you release the episode, you're
coming up on a year.
Indeed, yeah. So that's going to be quite exciting. And since then, we've put out quite a few demos. The library's seen quite a few updates. Lots of users. I can like go into some of the stats, which is quite exciting. Definitely really humbled by the community support for it. Definitely did not dream of it when I started it last year. So yeah.
It's honestly quite amazing. So like maybe we'll start with just like, for people listening, like understanding both what Hugging Face is as well as what Transformers is. And then we'll sort of get into the fact that you are making it work in JavaScript. So like Hugging Face, we've done, I don't know, probably 6 or 7 episodes on AI, and we touched on different points on of what they are. But Hugging Face, I like to say, is like the GitHub of AI, and it's a place where people can push their models. It's a people where people can push code. You can go through different options. There's lots of demos on there. It's a really cool spot to be on with when you're like sort of dipping into the AI world. Is that correct of how you would describe what Hugging Face is?
Yeah, absolutely. I mean, I guess like the tagline is sort of a collaborative platform for machine learning, where you can share, I guess, models, data sets, and applications that, I guess, and it's definitely very community driven, which is really great. You see all these people coming together, creating really amazing applications, all open source, open access models, and yeah, lots of the libraries that Hugging Face maintains, which is, I'll get into some of them now. I guess we'll start with, like, for example, Transformers, which is a Python library for running machine learning models locally, specifically Transformers, I guess, because, hence the name. Yeah. But we've seen like so many people be able to use the library to sort of create their own applications and build upon the library, and especially even like research groups being able to integrate their models into the library and just make it really, really easy for new developers to get started. I think it's at around 120,000 GitHub stars, which is amazing. Wow. I mean, the team is, wow, it's really, really something amazing. And then, for example, Diffusers, which is another library for running diffusion models. That one is also, I think it's around 25K stars. So many others. I guess the one we'll be talking about today is Transformers.js, which is a JavaScript version, I guess you can say, of Transformers, specifically to be able to run these models either in the browser, in Node.js, or any other, like, I guess, any other JavaScript environment, let's say like Electron. I guess that also uses Node.js behind the scenes. Yeah. But basically any platform, any environment that you want to run JavaScript, I guess, where you're running JavaScript.
It's quite amazing that you can do that. And I as soon as I found it, I was like, oh, like this is what I want, because like I know there is like TensorFlow.js, but I've had trouble getting that running in the past, and I've never really figured out like how to hook up models and whatnot. And this is me, a JavaScript developer with no data science background at all. I'm a web developer wanting to play with these types of things. And when I found Transformers.js, I was like, yes, absolutely, this is what I want. Because every time I had gone into like the machine learning AI world, I found like I had a pip Python install all this stuff and download 80 gigs of stuff, and everything was torch this and torch that, and everybody's telling me to use different things to install. And Python to me is, and it's mostly a skill issue, I understand that, but Python to me is such a pain in the butt to get running. And I always, whenever I'm like, I want to learn how this works, I find it really hard to get into. So you were just like, how does it even work? How are you able to just take a library that was written in Python and just like duplicate it and make it run in JavaScript?
Yeah, so quite a, like I said, it's been quite a long journey up until this point. But maybe I could provide some, I guess, context or a bit of an origin story for how the library sort of was developed.
Yeah.
And that might explain a bit of sort of where things are and where things are sort of going. So, like I said, around a year ago, I had a little side project that I was working on for, if you maybe have heard of this thing called Sponsor Block, which is like a browser extension that you can sort of, it's a crowdsourced way to sort of skip sponsorships that occur in a video, like a YouTube video. So aside from ad block, you're skipping segments in the video, like when the person starts talking about the sponsor of the video. What that sort of, I guess, and I've been working on this was like 2-3 years ago that I was sort of working on this thing where I trained a network because it's all crowdsourced. Yeah, all the data is freely available for us for anyone to use. And I trained a network to essentially do this automatically, be able to skip segments in a video automatically, which was cool, great. But the problem I was facing is that someone would need to either, let's say, run the server that would, run the model and then provide an API to the user.
Yeah,
that was something. Another thing is that I don't really want to be sending all my data to some API, especially this is from the user's perspective. They might not be comfortable with that. So that was an issue. And anyway, lots of things sort of, I guess, accumulated. And I was like, well, I would like to be able to run this as a browser extension. So I do some Googling. Nothing really exists to be able to run these models. The specific model that I was using, which was a fine-tuned version of T5. And I guess, well, the moral of the story is, well, okay, fine, I'll do it myself. So in like a weekend or two, I just put something together, created this little library, Transformers.js. It had support for BERT, T5, and GPT-2, which were like just a few of like 3 of the architectures that are currently supported now. And then what happened is I posted it to Twitter, like a weekend after I'd finished it. And next thing that happens, it blows up on Hacker News, gets like 1,500 to 2,000 GitHub stars in around 2 to 3 days, which was like, whoa. I know, right? It's quite a story to begin with. I didn't expect that at all. People just found it really interesting. They were like, well, this is really cool. What else can you do with it? I put some demos out, slowly start building the library. And to sort of get back to the question of how it's able to run, I guess an analogy would be that, so Transformers, the Python library, uses PyTorch to run the models, and Transformers.js uses Onnx runtime or Onnx runtime web to run the models. And basically Transformers.js, I guess you can say, like, simplifies the interaction with the library, sort of handling things like pre-processing, post-processing, all the everything in between, except for the inference, which Onnx runtime web handles, and then basically creating a very simple API for users to interact with. You may be familiar with the pipeline API, which is one of like the easiest ways to sort of get started with these models. And that was definitely adapted from the Transformers, the Python library, which makes it exceptionally easy for new users to get started. Basically 3 lines of code. The first one's like the import, the second one is creating the pipeline, and the third one is using the pipeline. So,
Wow. And I'm trying to, this is one of the questions I had for you, is just like, I understand what Onnx is, or like the fact that you're able to do this in the browser or in Node is because of this thing called Onnx. But I never really understood like what it is there for. Like, so your models, do they have to run in Python, or what language are the models, and what is Onnx doing there so it's available to run on different platforms?
Yeah, sure. So the reason I guess I sort of chose Onnx and Onnx Runtime, for those unfamiliar, Onnx is like I guess you can say like a standard for saving models. I think, what's it stand for? Open Neural Network Exchange, I think. And that's sort of a way to define the graph as well as the weights in a single file, which made it exceptionally easy to basically get things running, because you just load a file and as long as you supply the correct input tensors, it'll do everything in between. And another reason I chose Onnx Runtime, I guess I chose Onnx Runtime for this. So I guess the separation is Onnx is, I guess you can say, the standard, and then Onnx Runtime is a library developed by Microsoft for running Onnx models.
Oh, okay.
Which was very fortunate to me at the time, which I didn't realize in hindsight. Now I'm looking back on it, I was like, wow, this is really lucky that I sort of stumbled into this. Hugging Face actually already provided a library called Optimum, which made it extremely easy to convert the transformer models, which are defined in Python, in the Transformers library. Basically one command that you run to convert it to Onnx. And that sort of made it super easy for me to get started integrating models into the library. I guess I can go into more detail a little bit later of what that sort of entails, where basically providing a configuration file as well as like defining it in code to basically say, this is the type of model. Is it an encoder model or encoder only? Is it a decoder only? Is it an encoder decoder, or whatever possibility? Is it a custom thing? Is it like segment anything? We'll chat about all the demos later.
Cool.
But yeah, and just basic configuration elements that sort of need to be taken into account. And yeah, so that's why I was exceptionally lucky when it came to converting these models, because, well, the Transformers library already defines the models, and being able to add support for a new model was as simple as essentially, well, the first thing was adding a PR to Optimum, for example, just to say, this is the type of model, this is the inputs it requires, this is the outputs, and then running the Onnx conversion process, which is actually built into PyTorch, which is great.
Okay.
There were a few additional optimizations that sort of needed to be done. I guess I can go a bit into the details. Things like splitting, if it's an encoder decoder model, being able to split the encoder and decoder, just because of, well, there's a few reasons for that. The main one is preventing weight duplication, because in certain models,
I think that's probably over the heads of no,
too technical.
It's totally fine. It's really interesting, but I think like most of our audience is probably like, man, this stuff is wild when you really, really get into it, because like there's so many steps to AI and ML, like at a very level, like, oh yeah, I can ping the OpenAI API and get a response back, and then there's the next level, which is like, oh yeah, I can make some embeddings and query those values back, and then pass that to another one, and then the third level is, I can run them locally via Transformers.js. But like it's a pretty crazy world of how deep these rabbit holes go. Of
yes, would you like the red pill or the blue pill?
Yeah. So let's talk about just like some things you can do with this, because I think like people listening are web developers and they're building applications. And I think that a lot of people are going to this year want to start to run their models locally. They're going to want to run them on their own servers. They're going to want to run smaller models that are specialized for specific use cases. They're going to want to learn how to train their own models. So I think Transformers.js is probably a good use case for that. But one thing I really love about the Transformers documentation is that there's a list of all the different models and all the different categories of what you can possibly do. And if you just have a couple hours and you just want to like toy around with some stuff, just peer through that list and take a look at some of the demos that are there, and you can get some ideas for what you want to build. Because I think I've built probably like 9 different things now, which has been really fun. So like, let's just rattle through a couple of maybe your favorite, and we'll start with like the vision ones, where you can feed it an image and it's able to find things about that image, right? Like, what are some of your favorite vision ones?
Yeah, sure. So of the list that you're referring to, I guess like the supported tasks in Transformers.js, and currently we support 24 different tasks, which are spread over a variety of modalities. And I guess modalities is, you can just imagine as like the type of input or the type of output. So in this case, let's say text would be, text generation, text classification, relatively basic and traditional NLP tasks, natural language processing tasks. And then vision is the next one, which we'll discuss some of the demos. And then audio, so like speech recognition is a great one that people like to play around with. And then I guess the last one is multimodality, which is a combination of the previously mentioned ones. So to kick off some of the demos or some of the examples in the vision category, I guess the first one, which sort of, I guess you can say kind of blew up on Twitter, was someone made an object detection demo, which basically provide an image and it will predict bounding boxes for objects in the scene. I think it got like a 500,000 impressions in a few days, which is quite fun to see, and people playing around with it, creating more demos and more applications. And on top of that, I mean, the object detection demo, that was quite fun. And the ones I've seen you play around with, the depth estimation demo, which or the depth estimation task in this case, specifically it was using a new model which was released called Depth Anything. And because of its size, which was only around 45 megabytes at 8-bit quantization, and I'll discuss quantization later because it's a very interesting part to the process and how we are able to run these models in the browser.
Yeah.
But it basically, at 45 megabytes, you're able to load a model, cache it in the browser, run the model, refresh the page, and the model's still there and you can run it again. And it really enables developers to create really powerful, like progressive web apps or desktop applications, or the list goes on.
That's I want to be clear about that part, because I posted it to TikTok and all the comments were like, it's not actually local. You're just hitting an API from Hugging Face. I'm like, it's not though. It's downloading the model from Hugging Face. Thanks for the bandwidth, because some of these are huge. But it's like, right, it's literally running on your machine, and 45 megs, you're able to do depth detection. And then I piped that into Three.js and made a kind of a cool little pan around. And it's really good. Like, there's a basketball on my shelf behind me, and it picked up the curve of the basketball like 10 feet behind me.
Yeah, that's exactly right. And I think it's really something cool to show people. You literally turn off your internet connection.
Yes.
You run the model, and people are like, wait, what? How is this possible? So seeing that reaction from people, I developed a game for it. What is this? Like last year, called Doodle Dash. It's actually in the vision category as well. So I guess I'll discuss it a bit.
Yeah.
It's a real-time sketch detection game. So if you're familiar with Google's Quick Draw, which is like a very old demo from probably like 5-ish years ago, I would say, if I'd have to guess, maybe even longer, 5-7 years ago. It's basically Pictionary, but a neural network is detecting and predicting what you are drawing. And the original version, obviously, it would send it to an API. The request would be processed. It would run the neural network, say that you're drawing a skateboard, and then get the response back and say, I think you're drawing a skateboard. And then 5 seconds later, it would do the next prediction. However, for Doodle Dash, something I wanted to showcase was the ability to predict in real time. In the game, the neural network is continuously predicting what you were drawing.
On mouse
around
move,
60
right?
times a second.
Yeah.
Yeah, on mouse move, exactly. So 60 times a second in browser locally.
gosh.
And I think that really showcases the power of in-browser machine learning and, well, on-device machine learning, I guess, in general, where because there's no network step in between, you're really able to achieve these real-time applications. That was one of the demos, and surprise, surprise, that was actually running just in WebAssembly, no GPU, all CPU, which was quite surprising to see when it's running at 60 times a second. It's like quite powerful. And as we'll discuss later, where this is going with Web GPU, which is definitely something I'm excited for.
Yes.
And that's just going to make these models way, way faster. Get your depth estimation down to a couple 100 milliseconds, maybe less, tens of milliseconds possibly.
Let's talk
really,
about that
really
now, because
fast.
I'm super curious about that. So it runs either like I can run these models in Node and use just like save the file locally, or you can run them directly in the browser and you can view them. There's a lot of Canvas helpers that you can use to work with Canvas. And like another one I did was face segmentation. So you take a picture and it will segment it into foreground, background, eyes, ears, left eye, right eye. It's amazing that it's able to break it down into those little pieces. And sometimes they're really fast, and sometimes it takes, like the depth detection one took, I don't know, 10 seconds to actually run. And I was curious, like it's just running on like the CPU in the browser, right? And what's the next step to getting that to run on our computer's GPU?
Yeah, so that's definitely the next step. So Web GPU is an API that's being released. It's actually in many browsers already. The next step, I guess, is just being able to run neural networks with on Web GPU. So fortunately, the team at Microsoft who are working on Onnx Runtime Web, they recently released Onnx Runtime version 1.17, which basically enables Web GPU as an execution provider, which is going to completely, I think, in the next... It's difficult to say when, because integrating the latest version of Onnx Runtime Web into Transformers.js has been a bit of a technical issue, just because of ensuring compatibility with all the models. That's one of the things. There's a few, I guess, outstanding issues that are currently limiting being able to just simply upgrade the version. But we're really working closely with the Microsoft team to be able to get it working.
Yeah.
Around a month ago, we were testing out Segment Anything's, the original checkpoints of Segment Anything, which it's quite a large model. And basically computing the image embeddings would take around 40 seconds in WebAssembly. And that was just not possible, not feasible for being able to run it, I guess, on the CPU. But with the Web GPU backend, it would take around 2 to 3 seconds, which is significantly faster.
Yeah.
And on top of that, there have been recent improvements to the Segment Anything model and projects that follow on from it that have been able to reduce the size of the encoder significantly. And even in WebAssembly now, with the latest SlimSam variant of the Segment Anything models, that is able to take it down to just a couple seconds, like with your CPU.
That's amazing.
And this is around, I think the model is around 15 to 20 megabytes, which is surprisingly small. And that's one of the demos I released around a month ago, I'd like to say.
Yeah.
It's funny, the time is blending all together because all these amazing models that people are releasing. And
Just keeps every day there's something new. Yeah.
It does feel like it's every day. Yeah.
it's really quite something to keep up with. And that one, if you played around with it, it's quite fast, even on CPU. But that, because of the current, or when we eventually get the latest version of Onnx Runtime Web working, that would cut down the encoding time to a couple milliseconds, possibly tens or hundreds of milliseconds, which will be significantly faster. And on top of that, that's just the encoding step. And then you can decode in real time. So the decoding is around 100 to 200 milliseconds on CPU already. And bringing that down on GPU would be like tens of milliseconds, possibly even less than that.
Oh.
So there's definitely improvements to be made. There's definitely things that we're working on. Like I said, working closely with the Microsoft team to, I guess, stress test all these models, because we've got around 700 different models across 90 different architectures. And that is quite, yeah, like I said, it's been a long journey. Like we started with those 3 and slowly every week adding 1 or 2, slowly. And now we're at 90, which is quite something.
What about speed when you're running it in Node? So I imagine somebody listening right now says, okay, you know what? We're paying $6,000 a month for OpenAI. I think that we can replace that with running our own box. So let me go to DigitalOcean or wherever and spin up a box, or go to Amazon and get a GPU. Can you run that in JavaScript, or do you have to like exit out to Python if you really want to get into it?
Fortunately not. Fortunately, you're able to use Transformers.js in Node as well.
Yeah.
And when you're running in Node.js, you obviously get a lot more bang for your buck, shall we say, just because it's running at native speeds. There's no intermediate compilation step to WebAssembly needed. Many optimizations can be done now. Even on the image processing side, we use a library called Sharp, which is really efficient image manipulation library. And yes, that is possible. The Canvas API does a decent job, but it's limited in many regards. But back to running in Node, yes, there's many. It's significantly faster to run in Node. And when you are running these models on your own, instead of accessing it via an API, let's say you're considering generating embeddings with the OpenAI embedding API versus running it locally, let's say with Transformers.js. There's obviously speed implications, like the being able to run locally is amazing. The second one is cost, because $0 embeddings are significantly better than anything else.
Yes,
just because it's all running locally. So, and obviously, like I said, the model downloaded once, it's cached. You don't have to worry about it again. Don't have to worry about it being deprecated, which has been an issue in the past with various OpenAI APIs. And yeah, you're able to take control of the model, being able to use it locally, run relatively fast. I mean, some of the things I've created a few demos. One of them was with Supabase, a semantic image search application.
It's so fast.
Yeah, it is exceptionally fast. And I put out a few tweets about it. I was like, wow, this is really amazing. Do we need vector databases, or do we need vector databases? The short answer is yes, for millions and millions of embeddings. But for a small application, let's say 50,000 embeddings of images on your device, surprisingly, it processes exceptionally quickly, like less than 50 milliseconds to compute the embedding, and then be able to perform similarity search over all 50,000 in pure JavaScript. It's quite amazing. I was quite shocked when I did some of the benchmarking, and like I said, it's actually funny because I didn't do anything fancy. So I wrote 2 applications for this. The first one is server-side processing with Supabase, and the second one is client-side in browser processing. I guess just in JavaScript, vanilla JavaScript, nothing fancy. And that one was the one that was able to run at 50 milliseconds for computing the embeddings, and then doing similarity search across the 50,000, all running locally in your browser. No WebAssembly for the similarity search, no vector database, nothing. Just pure JavaScript. You can look at the code. It's actually really funny. The loading is just creating a new float 32 array, and then the search is just a simple for loop over the 50,000, which is it's not the greatest, but it worked really well for the application I was building.
Okay, because let me explain to the audience how impressive that is, because this is something that I'm going through right now with the Syntax podcast website and embedding. So the idea is there's 50,000 images from Unsplash, and I think the idea is beforehand you loop through every 50,000 and you convert the image to an array of random numbers. And the idea is that the machine learning model understands what's in the image. So if I search for dogs, or I search for red cat, or I search for long beard, somewhere in that vector, the AI understands that what are the pieces of that thing. And then once you have converted all those images, you can take a search term like dogs and convert it to a vector, which is a numerical representation of the word dogs. And you can compare that against an array of 50,000 vectors and just loop through them and use some algorithms, maybe we'll talk about that in a second, to see which ones are the closest to what you searched for. And I always thought like, oh yeah, you get over a couple hundred, you got to reach for like a special database that can do vector querying. But you're telling me you can load 50,000 of them in the browser and just go nuts with it?
That's exactly right. Yeah, the way you described it is flawless.
Wow.
Being able to essentially convert an image or text into a vector, just a bunch of numbers, and then as you're saying, the similarity, you call it a similarity algorithm, I guess. But in this case, it's this thing called cosine similarity, which is basically computing the angle between the vectors, which it works out mathematically. let's just end it like that. But yeah, it's just one of the ways. There's a few other ways. Luckily, if the vectors are normalized, you can just use dot product because it's the same computation as the cosine similarity.
Yeah.
But yes, as you're saying, it's just a way to be able to compare the vectors, and the way these neural networks are able to, I guess, do this. Specifically, I was using a model called Clip, which basically trains to associate similar images and their labels. So they've been labeled beforehand, a sentence for an image and its corresponding sentence or description. And then the neural network learns to essentially map each of these elements to the same location in the so-called latent space, which is just I guess you can call it a multi-dimensional space where these vectors reside. So the embedding that you get out, it lives somewhere in this latent space, just along these however many dimensions. Let's say 500, I think it's 512 or 768, just some arbitrary value. But being able to then convert these images or text or audio or videos or whatever element, whatever data you've got. In your case, I think it was podcasts or segments of podcasts, being able to map them into the space and then being able to perform search on the vectors in the space. Yeah, when you get into the details of it, I guess that's sort of what Transformers.js is sort of designed to do, is sort of abstract away some of these points so that users can use these models without necessarily understanding absolutely everything about the model. Because like you said, the rabbit hole goes deep.
It does.
It's really fun though when you can play around with these things at a high level. You can break them down and try to understand them at a lower level. It gets really fun. Like I said, some of the applications I've built, people have enjoyed them. They've done relatively well, but I think it's a fun creative outlet for myself as well, where I'm developing the library, but to showcase features of the library, I create applications, which then I guess you can somehow call it like some form of promotion, where you make these really fun applications with the library, and people see the applications, then they decide to go check out the library, and then more applications are built, and it's a
so
really fun vicious cycle.
Yeah, like honestly, like I know a lot of web developers get burnt out on coding, and man, if you want to have some fun and get reinvigorated on coding, check out some of this stuff, because it's amazing the amount of stuff that you can make just with, like, I think every single one of my applications is under 200 lines of JavaScript, which blows my mind that you can just build stuff with 200 lines of JavaScript. And like, not to mention that, like, I'm just a lowly web developer. Like, I didn't understand what a vector was. I understood that it's an array of numbers, and somewhere in those numbers, it describes that this is a dog, and some of those other numbers means that it's brown. But it didn't click to me until I realized, like, oh, like, yeah, you have 2D vectors, which is X and Y. You can have 3D vectors, which is, right? Like you have 3 points on them, but like the vectors that are coming out of AI are often like 1600 values. It changes depending on what the model is, but they're extremely long. And I was working on some 3JS code, and it clicked to me. I'm like, oh, those vectors are the same vectors as the ones I'm doing. And it's probably laughable to people like you, but just the guy who makes buttons on a website is really exciting to me. Let's talk about like maybe it's obvious to me because I'm very good at JavaScript. But like, why would somebody want to run AI models in a language other than Python or whatever native language they're meant to be run in, and being able to run it in JavaScript? What's the benefit there?
I guess from a developer's perspective, the benefits are quite vast. I mean, from things like being able to deploy your application as a static website, or even on being able to deploy it as a hybrid site where, yes, the server does processing of the customer's information, but sort of delegating some of the resources to the client so that they are the ones running the models. So as an example, if you host a website, one of your like a demo application on GitHub Pages, from the developer's perspective, there's zero cost involved because you upload the static site and anyone on the web can view it. Mm-hmm. I guess Transformers.js is able to take advantage of this, where the users of your application can then essentially contribute their compute to be able to run the models. And yeah, from the developer's perspective, I think that's quite an advantage because you're able to distribute your application, showcase your application without incurring quite large server costs.
Yeah, because it's expensive to run those servers, and like I even
especially
imagine
when you're running networks, neural networks, it gets quite expensive.
No kidding.
That's for
like
sure.
I think about like some of the image processing ones, and like if you wanted to like take, I don't know, 10,000 frames of somebody's video in the browser and convert those to embeddings, like you don't have to. That would be a major bandwidth cost alone to send that video to the server, process it, and get it back. If you can do that like we do it with image resizing already, it often makes sense to resize an image in the browser with the user's browser compute, and then send the smaller version of that image to the server to actually upload, rather than upload like a 15 meg JPEG to the server and resize it on the server. So you could see how that would work with AI models as well, right?
Yeah, exactly. And one of the example applications that we built and published recently was a background removal demo, where you'd upload your image, the network would predict what is foreground, what is background, and then segment the image accordingly. And many applications like this already exist. But the difference is that it's a static site. There's no requests made to a server. Your images aren't uploaded to a server. They're not stored anywhere. It's all running locally in the browser with your resources. And that's a major benefit for privacy-focused applications.
Oh, yeah.
When it comes to like, sensor data, let's say like webcam, microphones, I think from the user's perspective, they would be much more comfortable with a model running locally, not having their data sent to an external server.
Oh, yeah.
I think some of the other background removal websites, for example, they put little disclaimers saying your images are deleted after 60 minutes, which does say that your images are uploaded, then the background removal is run on the server, and after a period of time, your data is deleted, according to the website. And for Transformers.js models, it all runs locally. You can turn off your internet. You can, obviously, once you load the site, you can disconnect from the internet, run the model, and everything runs on your side. Yeah, and I guess another benefit of being able to distribute your applications on the web, well, since it's the web, it comes with massive reach and scalability. I think those are the two concepts that are sort of, what's the word, innocuous when it comes to web development and the web as a platform. Being able to distribute your software to millions of people just by them going to a website. Everyone has a browser, right? So you go to the website, you're able to interact with the website, versus pip install this, pip install that, dependency nightmares, you know?
Like even like not even Python, but like, so our editor Randy, we had to get him to install FFmpeg the other day. So I'm screen sharing. Oh, got to get Brew installed. Brew needs to get Xcode installed. All right, Xcode is installed. Now we need these weird permissions and stuff. And we got through it after about like 20 minutes. He got FFmpeg installed on his computer. And I was like, what we could have also done is just run ffmpeg in a WASM bucket, npm install the thing, and it runs directly in the browser. It takes all of the like complexity out of it. It's essentially a Docker image of just bundles it up into this nice little thing, and you don't have to worry about you have to worry about your user's browser that supports these features, and that's about it. Nothing else, you know? And it's beautiful to me that works that way.
Yeah, and I mean the problems when it comes to, let's say, showcasing what you've built, and it's just a barrier where people see it on Twitter. They're like, wow, this is really cool. Oh no, I have to install the application. I have to go through a million steps to... And from your perspective, the developer's perspective, it's like, well, no, it's really, really simple. You just download this, you install this, you know. But from the user side, it's just one too many steps for them. And I think being able to distribute on the web really, really makes that part of application development, not even just website development, more like progressive web apps. Let's say you're building the next Figma or something. I think it makes it easier for the developer and makes it easier for the user. And I think that both parties benefit. And on top of not having to install anything from the user's perspective, the browser acts as a sandbox where there are a ton of really powerful browser APIs. When it comes to the web audio API, the user devices, let's say webcams, location devices. There are a ton of very powerful APIs that you can access from the browser in a safe, controlled manner, which is important. And connecting that with machine learning in some way, let's say a webcam and you predict the depth, or object detection, or you record audio with a microphone and then send that to a speech recognition model. Being able to run, basically you can think of the browser as like a central location for all of these really powerful APIs, and then augmenting that with really powerful models, which really opens up Pandora's box of applications that can be built with this technology. I think it's really,
it's true.
really
like people are always like, "Oh, why use JavaScript?" I'm like, the APIs for accessing webcam, audio, streaming, server events, even like Bluetooth. I was doing some Bluetooth with this label printer the other day, and I took a Python library that connected to it, and the Python library for accessing raw Bluetooth, awful. Again, I'm not a Python developer, but I could not understand it. I switched to the JavaScript web Bluetooth API, and it's just the most beautifully crafted API ever. It's all promise driven. It's amazing. And I was like, these are really nice APIs. And if you can do that in the same language as where you're running your model, you can build really cool things.
Yeah, I mean, imagine, from a Python developer's perspective, having to worry about or add support for accessing webcams or screen recording. That's another thing that the browser provides. It's got a screen recording API, and just the amount of APIs that are being released and are available, it's just growing, and it's really, really powerful stuff. And you can imagine, from a developer's perspective, whether you would create an Electron application, let's say, and you would be able to access all these amazing APIs, as well as use Transformers.js, which is exciting. It runs in Electron. Or the other option is build, let's say, I'm trying to think of like the equivalent would be like a PyQt Python application connected to possibly a backend server that you'd need to run, maybe running Flask or something. There's many options, there's many alternatives, but I think being able to access these very powerful APIs with just a few lines of JavaScript, and then on top of that, run neural networks. I guess that's what Transformers.js is built for. It allows them to create really powerful applications for progressive web apps, Electron applications, websites. The list goes on.
Yeah, amazing. And actually, that's a follow-up question I have is, if you're building this stuff into an Electron app, obviously Electron has Node and it has like a Chrome instance. Where would you run Transformers.js if you have the option to do both and they're both running locally?
When it comes to those two options, I would definitely recommend to use the Node backend simply for performance benefits. But yeah, if you're the user can decide what works best for them, depending on what APIs they need, whether they need it sandboxed.
Sandbox environment.
Options.
Yeah, there's a lot. It's so nice that you can run them on both sides. Let's talk about the actual API then of Transformers.js. What is the idea of a pipeline, and what does the API look like?
So at a high level, the first thing that I would recommend that users interact with is the pipeline API, which is basically a function that returns a so-called pipeline. And I'll explain what that is now. A pipeline is basically a way of moving data throughout the network, both with the pre-processing, the actual running of the model, and then the post-processing. Fortunately for users, this is something that they don't have to worry about, but I think it might be worth just explaining in a bit more detail. Yeah. The user would basically create this pipeline, and behind the scenes, all these things will be constructed. So then the 3 steps. So the first one is the pre-processing, which, for example, takes the text and generates tokens. The next one is the model inference, which is the actual running of the Onnx inference session. And then the final thing is the post-processing, basically turning it into a format that is easy to understand for a user, because the neural network understands tensors. You give it tensors, it outputs tensors. But for the user, that's not really helpful. So for example, with let's say an object detection pipeline, you would like to give it maybe an image or a URL of an image, and what it outputs is that you want the bounding boxes, for example. So you want sort of like the minimum X, the minimum Y, maximum X, maximum Y for each element that's been detected. And that's what the pipeline post-processing takes care of. So you would take the tensors that are output by the network, and then it would format it into JSON, which a user can easily interact with. I think some of the examples you've maybe seen are with image segmentation, possibly. You would get a list of, let's say, images that would be output from the pipeline. Or
it'd be like right eye, left eye, and it also gives you like points where they go, and then like you have that raw data, and then you can do whatever you want with it. And there's a bunch of helpers, right? Like you can write it to a canvas, you can download the JPEGs, you can use it as a mask if you're using a canvas. It's really neat. Yeah.
And I mean, for simple things like text classification, it would output, let's say the actual the label that it predicts, as well as the score, let's say. So, and you can use that information how you will. And there's a bunch of parameters that you can set that will allow you to control how you want the model to run, and additional things.
So there's one really small model, I forget the name of it right now, that does object detection in images. What is the
Detter, probably
ResNet. That's the one. So that's the one I use in one of my upcoming courses, just because we're building a silly like hot dog detection app, and it tells you put something up to the camera, and very quickly it's able to detect objects in the actual image, and you can do it fast enough that you can actually run it on the frames of the video, and then it'll be like, 80% I think this is a hot dog, and 20% I think this is a Band-Aid. Like it'll think, like, we all know that the AI thinks that sometimes it's the wrong thing, but that score or like sentiment analysis as well is like, we ran it on frames of the video from Scott and I, and then we can sort it by we can filter for happy or filter for excited, and then sort by the highest probability that that's the sentiment that is shown in that specific video. So it's really cool that you also get the raw data behind the results as well.
Yeah. Hey, Wes, and you mentioned like if people want to get invigorated, they can jump in and try some of this stuff.
Yeah.
What's the like the number one easiest thing they can get up and doing?
Oh man. For me, it's always webcam stuff. It's always like audio or video, something. I would probably maybe try like a speech to text. It would be kind of interesting.
And what's the process there? They install.
You go to the demo, you copy paste the example code that's on the Hugging Face website. And then I just usually have like a Vite index.html, or I'll run it on Node. you just start changing things around, right? And you don't have to download the models or anything like that. It's part of the sort of boot up script. And you're up and running. I have a whole bunch of examples up on my hot tips repo as well, but I would just grab the samples from the Transformers library.
Yeah, actually, on the GitHub repo, you can actually check out some of the examples that we put out. So all the demos that you see me post on Twitter, for example, I post the source code is always linked on the GitHub. And for example, the Whisper Web demo. So you were talking about speech to text.
Yeah,
that was actually one of them. That was probably the first viral demo that we put out. I think it racked up around 2 million impressions in like a couple days, which was astonishing. I was not expecting that at all. And it's basically, for those unfamiliar, OpenAI released a collection of automatic speech recognition models called Whisper. And one of the models, well, there's a collection of them, but one of the models is relatively small. It's named Whisper Tiny, and at 8-bit quantization, it's only around 40 megabytes. So loading that into the browser was much easier than, as you were mentioning earlier with the dependency nightmare with pip, all these fun things. But from the user's perspective, them not having to go and install anything locally, everything's running in the browser. There's no installation required. You just visit a website. And I think that's what people were quite interested in when we released the demo. Basically, being able to record your voice or upload a file, and for the web page to basically spit out what you said with no API calls, other than obviously downloading the model first. There's no calls to an external server. Everything was running locally, and the speed was quite fast. Like I said, everything with WebAssembly, and later on when Web GPU support is added, we're probably going to see some real-time speech recognition, which is really exciting to see. We've actually got some things cooking, which I won't spoil, but
that's awesome.
That's definitely the biggest one on the list, because it's the thing that people were quite amazed by when they saw first, where, well, wow, this is amazing. Whisper Web running OpenAI's Whisper models in the browser, no downloads, no installation. It was quite fun for people to play around with, and being able to sort of take that further and being able to get real-time transcription is something that we're definitely looking at. I think it's the biggest application that we're looking forward to adding.
Yeah. What about models that are? I think right now there's a limitation with Onnx or something where it's like 2 gigs is as big as the model can possibly get. And I went down the rabbit hole. I was like, I want to run Stable Diffusion, because Stable Diffusion is the huge model that if you see people have these AI headshots, or you see any of the stuff that Peter Levels is putting out, where he has all these like cool things where you can generate interior photos of design and headshots. Those are all running on Stable Diffusion, and the Stable Diffusion models are 9-10 gigs, something like that, and they produce some of the best results that are open source. At least like the Midjourney stuff is pretty on par with it as well, but Midjourney is not open source. Will we ever be able to run Stable Diffusion via JavaScript? I've seen some demos, and I tried to get it running, but I hit a lot of issues.
Yeah, so at the moment, so the short answer is yes, that these models are already running in the browser, but there are, as you've encountered, some issues. So you may need to enable some Chrome developer flags, or you may need to, I think one of the flags like disable robustness, which is not ideal. You don't really want, it sounds like you shouldn't do it, but just a bunch of things that extra steps you need to go to. Getting the 64-bit WebAssembly running, as you've encountered, there's a few more steps that you need to take. But those versions are being updated. I think it was a Chrome 122 was released today, I think it was, which improves Web GPU support, which is great. I think a while ago they also added FP16 support, which is desperately needed for these models, basically cutting the model size in half, but getting very similar performance.
Interesting.
And many other things. So just to elaborate on what you were saying earlier with these basically at the 2 gigabyte limit. At the moment, that's basically just because of, well, there's two reasons. So the first one is the 32-bit WebAssembly address space. So it goes up to 4 gigabytes, but due to a bug in Onnx Runtime Web, we weren't able to access memory over the 2 gigabyte limit.
Okay.
That's been fixed now, but it hasn't been fixed in Transformers.js yet. So that's one thing. And then the second one is when you convert to Onnx, due to the way it's saved, called protobuf, the model itself, if it goes over 2 gigabytes, you have to split the model into the weights and the network definition. And previously, currently, I guess, with Transformers.js, but this has now been fixed in the latest Onnx Runtime Web version, you weren't able to load the weights separately. You'd need the single file. But as I've mentioned now, 1.17 is out, which fixes all those things.
Yeah.
Really exciting. And gets the address space indexing is working, and the web GPU support is nearly there. I think it's good enough to upgrade upgrade Transformers.js to 1.17. So we're definitely going to be doing that soon. But yes, so many of the limitations that are currently faced will not be faced shortly or soon, whenever we are able to release the next version. The next major version, which we will dub V3. So maybe when the podcast comes out, V3 will be out. Who knows?
Okay.
We'll see. Yeah, it's really nearing that point, and it'll definitely allow us to run significantly larger models at, I guess you can try to say near native, but there will always be a bit of a performance like degradation on top of these the models when you're running in the browser, but as close to native as possible. And for people listening, they might want to check out the Web LLM project.
Okay.
They have definitely, I think they're the forerunners for running models on web GPU. They've done some amazing work with running like large language models like Llama, some of the Mistral models, as well as Stable Diffusion. So they've got the Web LLM and the Web SD projects that they've got running, and those are able to run these really large models in the browser, similar to what Transformers.js is trying to achieve.
Wow.
And yeah, they've done some amazing work. Really encourage everyone to go check them out as well.
That's good. I'm very tempted to try it while we're on this call, but I do not want to crash my browser,
Yes, it's going to load a very large model.
Yeah.
And they've been able to, if you're running on a Mac, they actually basically allow you to run Llama 70B in the browser, which sounds like unbelievable. Yeah, at various quantization levels, they're able to achieve it, as well as, I guess that's just like the general takeaway is that you're able to run exceptionally large models in the browser, which is really exciting for what's to come next.
This is so exciting to me. Like, not even just the browser, like that's exciting as well. But like, if I think about, we want to be able to auto generate thumbnails for our YouTube, right? And like imagine we could take a couple photos of Scott and I, and then feed that into the model and be like, all right, like, given this is what we look like in this episode, can you like make us look at turn our gaze towards the actual user, or touch it up, or like apply some sort of effect where Scott and I are anime in one of them, you know?
YouTube face.
Yeah, give us YouTube face.
YouTube thumbnail face. Yeah.
And like, I feel like we're so close to just regular script devs being able to do this type of thing.
Yeah, for sure. There are so many applications that are waiting to be built. I mean, even on top of some of the stuff we were talking about earlier with some of the vision demos. One of the actually it was a Discord community member posted on the Discord saying, "Hey everyone, I created a Vision Pro app that basically takes and uses Transformers.js to produce. It uses one of the depth estimation models to basically turn an image into, I guess, 3D, and then view that in Vision Pro." And sort of the thing about, or considering, or even thinking about just running this in the browser, like going to a website and being able to do these things is really quite something. I think his example was a desktop application, but you can definitely see how this would, I guess, people creating very interactive websites, and a benefit is that you can export as a static website for which is a huge benefit to web developers on a budget. You can
Yeah.
upload your site to GitHub Pages or whatever, and be able to run these really powerful models, zero cost to the developer in that sense. I think it's quite something, quite a benefit that Transformers.js provides.
Okay.
So that's lots of fun things that are waiting to be built.
Yeah. So one thing that we want to build, and I've started working on it, and you've helped me out on Twitter, but I kind of want to explain what we want to build for the Syntax website, and sort of get your thoughts on like how should we tackle this. So we have 700 and what episode is this right now? 737 episodes of Syntax, right? And discoverability is an issue once an episode is more than 4 or 5 months old, right? So what would be cool is if we could somehow we have transcripts already of every single one. We have every single utterance, which is a couple sentences Scott and I have said, but we want to be able to use AI to categorize and group together the episodes of what we have. So we want to just be able to feed it all of the different transcripts, feed that into some sort of model, and for it to spit out both like groups, like these are about JavaScript, these are about AI, but figure the groups out for us, as well as have some sort of like related episodes. So you're watching this episode right now, you're like, I would like to hear a couple more AI episodes. Show me the ones that are the closest to this. What would be your way to tackle this project that we want to do?
Yeah, sure. I mean, off the top of my head, the first thing that comes to mind would be using the Sentence Transformers library, which is also now maintained by Hugging Face, otherwise known as SBERT. You may have heard about it or played around with it. They've got a few demos and example notebooks showcasing topic modeling, which is, as you described, the problem of, given a bunch of text, find topics inside of the text and basically perform clustering on that. So there's definitely a bunch of resources and tutorials out on it. But if I would have to tackle it, let's say, outside of that, you would then possibly, as you say, segment the transcripts into however many, you said, how many, 700 odd podcasts, all with utterances for each podcast, which could probably total like hundreds of thousands of words. Easily. Yeah. So, I mean, hopefully you would have segmented them. You mentioned utterances, but if there's an additional way to segment, possibly on maybe the labels you attach to various, let's say, if I remember correctly, on YouTube, you have like the various topics that you have. So if you have already defined labels, that could be useful.
Oh, okay.
You would basically try to segment such that you don't overlap concepts, because if you're able to do that, then when you generate an embedding for each, let's say, sentence or maybe a paragraph, if you are able to do that without overlapping, then the embedding would hold a better meaning, or the semantic.
Okay.
How would you describe that? Let me think.
Yeah, like I think I can understand it. It's like I'll answer it with the problem I was having is I tried to convert every single utterance to an embedding, but I found those were too small. So I tried to convert the entire episode to embedding, and that was too large. So what I tried to do was find an average of all the embeddings in the show, and that got really washed out because we talk about many things in the episode, and you lose some of that topic one. So what you're saying is like we already use AI to figure out what are the major timestamp topics of the episode, use those to chunk it into individual topics, and then convert that to an embedding? Yeah,
sure. So I guess the problem you're describing is like this idea of granularity, where because you're basically taking a huge amount of information and basically saying, okay, you've got 768 values to represent everything. Well, the embedding just basically becomes a blur of what happened in the episode. So being able to segment in a way where the chunks are their own concept is very important. There actually has been quite a lot of work on automatic creation of these segments. And one of the approaches is, yes, what you do is that you create an embedding for every sentence. And then what you do is that you, for each consecutive sentence, like you got these short phrases where you do embeddings. Yeah. And then you perform, let's say, a cosine similarity between these two. And if it's under a threshold, whatever that threshold may be, you join the segments, say, okay, these are basically the same topic, and you put them together. And what you find is that depending on you, there's a bunch of settings and parameters you can play around with. But what you can do is you'll see that when there's a cut in the topic, or when you're talking about something and you switch over to a different topic, that would then be put into a different bin than the others. And in that way, you're able to, let's say you talk about some topic for 3 sentences. They're each linked to each other. The similarity scores are in this case, above some threshold, let's say above 0.5. I don't know, I'm making up a number. But you can choose it later on where you can say, okay, merge all consecutive segments where the similarity score is above 0.5, 0.75, whatever the number may be. And you'll get a bunch of segments. And those then you can generate embeddings for, because they're closer, they're better related to each other. Yeah. Each segment, which are now a collection of, let's say, 3 to 5 sentences or utterances, whatever the transcription model produces, those will have a better meaning together. So then what you can then do is generate embeddings for each of those, and use that for when you perform the search. You'll take the user's query or a part of a podcast that you already like, take that embedding, and then perform a similarity search across these slightly higher segments. It's not the highest granularity where every sentence, or in the extreme, it would be every word that you're embedding, which is not ideal. You would then be generating for every paragraph, let's say. If you're able to generate a paragraph, that's the ideal. You generate these paragraphs and then do similarity search across the paragraphs and then suggest users based on that. I would also then say that there are some possible issues with this approach, is that typically the current embedding models, they implement this idea called mean pooling, where also please stop me if I'm going too technical.
No, I'm curious. This is very selfish of myself. I just want to hear about it. Yeah.
Yeah, sure. We can cut it out later. So for transformer models, the way embeddings are computed are on a per token basis. And then at the end of that, an operation called mean pooling is typically applied. And the pooling mechanism could be, there's many options. The one is class or CLS pooling. Max pooling, or there's many other options. But the idea is that you have a bunch of per token embeddings, but you want one embedding for the whole sentence. So you basically, mean pooling in this case would be averaging all the embeddings, which sounds great and all, but you're essentially blurring the topic. Okay. So that's not ideal, because you potentially lose information. But it's nice so that you can compute and basically compute embeddings for sentences of variable length. So you could have 100 words, or let's say 100 tokens versus 50 tokens, but you can compare the embeddings, which is why people apply pooling on top of the per token embeddings.
There could be an issue because if I'm saying the word render in one sentence, it might be very important in that one sentence. But if I say render in a different sentence, it might be not all that important to the actual topic of the sentence. And it's hard to sort of figure that out because it can get washed out in, I know we're not supposed to say words and averages and whatnot because there's some data sciences behind it, but that's how I kind of understand it.
Yeah, that's definitely how, that's one of the pitfalls of using basic pooling mechanisms. Something that you might even be interested in now is it's a new model or a new technology, I guess you can say, called Colbert, which basically tries to solve this problem by using sparse representations of the embedding of the outputs of the network. And I'm definitely not qualified enough to be able to discuss it in enough detail. But I know that those types of models are working to solve this problem of essentially blurring all the embeddings together. And possibly, and I was sort of getting into it, where a possible problem with taking averages of averages is that everything gets washed out and you don't really get the true meaning. But for applications that I've developed, these approaches generally work quite well. One of these applications that I developed quite a while ago was before YouTube like put their foot down and decided to help remove spam comments on YouTube videos. Before then, there was a real issue of, I mean, there still are these days, but it was way worse a few years ago. There would be all these scam gift card giveaways in the comments.
Yeah.
And what I did, I basically downloaded around 10 million comments and performed with sentence transformers, performed clustering on it. And so it's actually funny because this is before LLMs, so before the current generation of LLMs.
Yeah.
So basically, scammers were quite lazy because they would basically repost the same comment over and over, and you would be able to cluster it and then identify what is spam and what is not. However, nowadays, I guess the topic of that is it's not as easy. But anyway, what I was getting at is that for these very simple approaches, I used k-means clustering.
Okay.
It's something you've played around with, I've heard in a previous podcast. And that worked really well for my application, and it's a great way to get started. So I think for people who want to play around with these things, start with the most common, most simple application. If it doesn't work, move on to something more complex. But you can get a lot done with really simple, architectures.
Yeah.
Like I said, with the 50 milliseconds for similarity search across 50,000 images. And it's amazing because you search with text and you get an image back. And that runs in the browser. Yeah, we've discussed that.
The k-means thing is really interesting. I want to touch upon that for the audience because I think that will be really interesting for people who do want to group together. So like, I'm at the point now where I have converted all the episodes to embeddings, and I ended up with an embedding for the entire episode. And the granularity is not great. I have to go back and implement some of the things we talked about today. But then you pass that to the k-means algorithm, and you can say, all right, take these 100 episodes and group them into 6 buckets, right? And it will try to like draw a circle around these 6 buckets, and it'll give you, all right, these ones are similar. And as poorly as I did it, it ended up giving me pretty good results. And then I figured I was able to then take the titles or something interesting about the episode and then feed that back to another AI and say, can you describe this in a single topic? Or like, why are these episodes similar to each other? And then it would give me back some text or something. Is that kind of like the last step of what you do there?
Yeah, that sounds pretty good. I mean, I would I would like to spend a little bit more time to delve into the details and see what you guys are doing. But yeah, those are definitely many approaches. I think the ways I've sort of been describing it, the ways I've described it right now are sort of, I guess you could call the traditional ways of. This was many years before, many years ago, before the current generation of GPT-4 or whatever.
Yeah.
And there's like the more traditional approaches. But yes, as you're describing, it sounds that definitely sounds like using the new technology to your advantage. I think being able to allow or ask these LLMs to generate topics for you instead of having to go through the hassle of topic modeling with sentence transformers, or just paste it in. Hey, what are the topics in this thing, and then it gives you a list of things, which is quite cool. And then automating that possibly with with the API or lots of approaches.
Super cool. Before we wrap up here, is there anything else? I'm sure we could talk another hour about this stuff, but is there any super important stuff you absolutely wanted to cover?
Yeah, I think one of the things possibly is the idea of quantization. Maybe.
Yes.
That could be interesting.
Yeah, let's hear it.
So a key point to be able to run these networks in the browser is the idea of quantization, which you can think of as like a compression technique, which reduces like the compute and memory costs when performing model inference. This is typically done by representing the weights of the network with lower precision data types, something like int8 instead of float32, which is like the normal the normal data type used. And obviously you have even lower, like int4 or lower, as well as like float16. So there's many approaches to decide how you store the network. But this is really important for in-browser usage because you're able to cut down the memory costs by a factor of 4. So taking 32-bit floats and bringing them down to 8-bit integers. It's a compression factor. You get 4 times less. 4 times the model size is reduced 4 times, while performing pretty well. And I say pretty well because there are compromises. Maybe the performance does degrade, but you can still get pretty amazing performance for all the models. So actually all the demos that you've seen me put out are with 8-bit quantization. So everything works surprisingly well when using a less precise data type. And it also assists with speed because you can, I guess the CPUs nowadays have got really, I guess, how would you say, they're able to compute integer multiplication very fast, especially with matrices. And being able to compress the models by quite a large amount is able to reduce bandwidth costs to the user, because obviously they have to download the model, and no one really wants to download like a gigabyte model and then close the tab and it's gone. So being able to reduce it in size is one thing, and the speed is also another thing, which really makes quantization necessary for in-browser usage.
Wow, that's really cool. It's not often you think about numbers in JavaScript, right? Like you usually just you make a number and you move on with your life. And then we talked about it on the database show where you get into MySQL and there's all these options for different kinds of numbers that you need to go with. But you can use the different. We have big int now in JavaScript as well, and obviously you can do 8-bit. So that's really neat that makes such a difference.
Definitely something that's needed. You need for running these models.
No kidding.
I mean, all the tokens when you generate token or you tokenize text.
Yeah.
Everything's represented as big ints.
Wow.
Just because the way the models are exported and things like that. Fortunately for users of the library, they don't really have to worry about that.
Yeah.
They can just perform, like you run the tokenization either with the tokenizer or inside of the pipeline class.
All right. Well, we're heading up on an hour right now. I probably could talk to you for hours on end, both because of that South African accent, but also because of how smart you are with this stuff. But we'll put this out to the audience. Like, there's obviously a lot to learn here. And I think it's kind of interesting for web developers to dip their toes into some of this more advanced stuff. So if there's interest for this type of stuff, if there's specific spots that the audience, would like to learn, let us know. We can certainly have you back on to learn about that. But for now, let's move into the last section of the show, which is our sick picks and shameless plugs. This is a section where we recommend something that is sick, and as well as plug out where people should find you online.
Yeah, sure. I guess my sick pick for the week would be Web GPU. Basically, just everything to do with Web GPU. I think that's one of the technologies that's going to help shape the future of web machine learning. There's many demos that you'll hopefully be seeing soon. I really think there's a ton of potential for applications being built by web developers to be able to bring very powerful neural networks, running them in the browser at near native speeds. I think the prospect of that is really something to look forward to.
It's going to be dangerous given the JavaScript nerds access to the GPU, I'm really excited to see what comes out of that.
That's for sure.
And what about a shameless plug? What would you like to plug to the audience?
Probably my only shameless plug would be to follow me on Twitter, or X, whatever it's called these days.
Yeah.
Xenova.com. So yeah, that's my shameless plug. And if you want to, you can check out the Transformers.js library.
Great. I highly recommend a Twitter follow as well as checking out the library, because there's always interesting things popping up that you're tweeting, it's really neat to have a peer into this different world. And we're used to buttons and clicking and submitting form elements and talking about frameworks. So it's pretty exciting. Awesome. Thank you so much for your time. Really appreciate it. And I'm going to spend the rest of my day playing with this stuff. Thank you.
Great. Thanks for having me.
Peace.